composite number before I get into this proof. So 8 is a composite number since it's equal to the product of two numbers that are not equal to 1 or 8. All right, so 8 is equal to 2 times 4. All right, and notice that 2 and 4 are both strictly between 1 and 8. Okay, so 1 less than 2 comma 4 less than 8. And that's what we mean by a composite number. If you have divisors other than 1 in the number itself, you are considered a composite number. That's it's the opposite of prime. Okay, so there we go. And again, 8's just an example of a composite number. Now, what we're trying to prove tonight comes straight from a number theory book by a well-known author. Let n be a composite natural number. Let p be the smallest prime factor of n. Notice any composite number has a prime divisor. Any natural number has a prime divisor. Now, we also have this relatively strong condition that smallest prime divisor or factor is going to be greater than the cubed root of the number itself. All right. So we're supposed to prove that n is equal to p times q. Now, in Dudley's book, he wrote this as n over p. And I think I know why he did it. We'll talk about that later. But n over p is prime. Now, it's equivalent to this, actually. But n over p is prime is how it was stated in his book. And this is equivalent to that. P and Q don't necessarily have to be distinct. That's the key thing here, I think. All right, now, so here's how the proof goes. We're going to assume that that's not the case. We're going to assume that n is equal to a multiple of p, not two primes multiplied against each other, but n is a multiple of p, where m is composite. All right. Now, again, we already know what composite means, so we can conclude that m has a prime divisor greater than p. And it has to be greater than p because p is the smallest prime divisor of n, right? So we're saying that n is equal to mp. That makes m a divisor of n, right? So that means that m has to have a prime factor that's greater than the smallest prime factor of n. Okay, so in other words, that prime divisor would be this P1. Now I'll just label it right here, P sub 1. Okay, so and also if it's a divisor, it has a corresponding composite factor pair, if you want to call it that. Okay, so m has a prime divisor. And we just labeled it like this, y'all, m sub 1 times p sub 1. Okay, again, this is just m, and we use this condition, this very strong condition that p is greater than the cube root of n. Okay, now what we can conclude right here is if p is the smallest prime divisor, okay, so p1 has to be greater than p. All right, p1 must be greater than p. Right? Now also notice that this also means that m would have to have a prime divisor since m is composite, right? M sub 1 would have to have a prime divisor since m sub 1 is composite. So that also implies that the prime divisor would be bigger than p, which in turn implies that m sub 1 is greater than p. Okay, so let me write that right here. M sub 1 is greater than p. Okay. All right, but what does that mean? That means that this is greater than p, this is greater than p, so this has to be greater than p cubed. Right? But that's clearly a contradiction. It's clearly impossible. We have p cubed is greater than itself, right? So what does that mean? That means we have to conclude that n is equal to q times p because we assumed that M was composite. All right, but it's we just reached this absurdity right here. Okay, so that means that N is indeed equal to 2 primes, the product of 2 primes. Okay, again, y'all, I am assuming that Q is a prime, but I hope you see the logic here is kind of nice. If we assume that M is composite and we reach this contradiction here, that means that N cannot be a composite times P. It has to be another prime times P. And let me just write this down for clarity. I've written it down once, but just to be sure, Q is prime. Now, nowhere in here have we done anything that indicates that Q and P can't be equal to each other. And I think that's why Dudley wrote it this way, perhaps. Not sure. Okay, now let's take a look at some problems or some concrete examples, because this is sort of abstract. Let's say we have N is equal to, let's say 3 squared. Okay, now this is not strictly in the form, and let's see why it isn't. Okay, let's say 3 squared times 7, right? 3 squared times 7, right? Now that's equal to 42. Okay, but notice that in this context, in this setting right here, okay, what are we assuming? That P is greater than the cubed root of N, right? Well, our P here would be 3, so notice that 3 is not greater than the cubed root of 42. Okay, folks, and by the way, this completes the proof right here. I should have written QED right here, but I'm just going through some concrete examples right now. Or this contradiction means that N has to be the product of 2 primes. Okay, now let's look at one other example here. And notice, y'all, the cubed root of 42 is definitely greater than 3, since 42 is greater than 27, right? All right, so now, but let's take a look at a case that fits the criterion. Now, right here, that's equal to 20, whoops. Okay, that's equal to 21 right here. And notice that 3 is greater than the cubed root of 21. Now, it's not saying every time it's in this form, and let me give you an example of that. It's not an if and only if thing. Okay, let's try out, let's say N is equal to 3 times 11. Okay, that's equal to 33, right? And 3 is not greater than the cube root of 33. Whoops, 3 is not greater than the cube root of 33. Okay. Now, just in a cool little thing here, it's not necessary that Q and P are distinct. And let's just look at just a general statement. If N is equal to P, okay, if we have N equals to P here, okay, notice P squared, excuse me, N equals to P squared. or it's PQ, just take P equals Q equals P if you want to. So if n is equal to P squared, right, what does that imply? That implies that it's always going to be the case that P is greater than the cubed root of P squared. And that's crystal clear, isn't it, folks? P is greater than the cubed root of P squared. So this form always works. But anyway, y'all, I hope you liked that. I thought it was kind of abstract. I liked it a lot. I thought it was really, really neat because you just started with this abstract statement about cube roots. Then you realize that this form, this is the only form which is it encompasses any prime squared. So that's the only form for this relatively, I guess this is a very strong inequality because this is the only time something like this can happen. Okay, that's it.